Welcome to the second part of this module, where we will start by discussing the core components of precision agriculture. PA is not merely a single technology, but rather a system defined as the use of computational and information technologies to enhance agricultural profitability and sustainability. It is often associated with technologies that facilitate a transition from field-level to subfield management in mechanized farming. While new technologies introduced innovative processes, the fundamental principle of PA lies in understanding and managing variability. PATs enable more precise management of in-field variability. Tools like GPS and GIS are commonly employed in PA, allowing farmers to minimize inputs and maximize cost efficiency by utilizing modern technologies instead of traditional methods. Additionally, VRT has been introduced to further enhance precision farming practices. Firstly, the declassification of GPS for civilian use and the development of farm-specific GIS in the early 1990s are widely considered pivotal milestones in the evolution of PA. Among the earliest and most enduring GPS-linked farm technologies are LightBar and AutoSteer systems, which assist farmers in plotting efficient field routes. AutoSteer, now one of the most widely adopted PATs, is a form of quasi-automation that uses GPS and GIS to map fields and organize routes. This system minimizes row overlap during planting or harvesting and reduces the manual effort required from farmers, providing significant relief during field operations. A second key component of the PA system is field mapping, which underpins many advanced precision technologies. Companies such as John Deere, AGCO, and Monsanto's Climate Corporation provide proprietary mapping software that integrates satellite or drone images of fields with data layers, including yield maps and historical profitability records. These data layers form the basis for management decisions and enable the integration of other PATs. For example, VRT, which allows real-time adjustments to seeding rates or pesticide applications based on spatial data, relies on these mapped computations. VRT works in harmony with GIS, AutoSteer, and field mapping. Farmers can overlay yield maps with soil quality data, develop tailored planting, spraying, or watering prescriptions, and upload them to planters that adjust application rates dynamically as they move through the field. Surveillance and monitoring technologies represent a third essential component of modern PA systems. These technologies are diverse, ranging from overhead sensing, e.g., multispectral imaging, light detection and ranging, LiDAR, and normalized difference vegetation index, NDVI, via satellite, drones, or planes, to real-time soil monitors and machine-mounted sensors on tractors or irrigation systems. They also include radio frequency identification, RFID, for tracking livestock and equipment, behavioral monitoring and biological assessments of livestock, such as stomach content and excrement analysis. Many of these sensing tools connect to integrated management platforms like John Deere's Operations Center. For instance, aerially sourced NDVI data can measure chlorophyll reflectivity to identify crop stress areas or provide precise nutrient treatment recommendations. When integrated into PA platforms, these analytic and algorithm-driven prescriptions combine with other data layers to create a comprehensive, data-rich view of field conditions. This holistic approach fosters confidence among some farmers in these aggregated, algorithmically regulated insights, viewing them as more accurate and precise. The development and implementation of PA, or site-specific farming, have been made possible by integrating GPS with GIS. These technologies enable the seamless coupling of real-time data collection with precise location information, facilitating the efficient analysis and management of extensive geospatial data. Global Positioning Systems, GPS technology. Monitoring and conducting agricultural activities across large areas often requires precise positional information to optimize operational costs and minimize completion times. Accurate positioning is crucial for managing large farms remotely, and this need is met by the GPS, which provides the precise location data necessary for sampling and analysis. GPS-based applications in Pennsylvania are widely used for tasks such as agricultural planning, field mapping, soil analysis, crop monitoring, variable rate input applications, and yield mapping. GPS technology enables farmers to operate effectively even under low visibility conditions, such as rain, fog, dust, and darkness. Many farmers now rely on GPS-derived tools to enhance their farming operations by mapping field boundaries, irrigation systems, and problem areas like weed or disease infestation. The high accuracy of GPS allows for precise farm maps, including field acreages, road locations, and distances between key points. Additionally, GPS enables farmers to revisit specific field locations for tasks such as soil sampling or crop monitoring, ensuring consistent and efficient management year after year. In recent years, GPS technology has become increasingly significant in conserving land and water resources. Advanced GPS tools facilitate sustainable resource management, offering practical solutions, flexible decision-making tools, and robust data analysis systems. GPS satellites transmit signals that allow receivers to calculate their location in real time, providing continuous positional data while in motion. This precise information enables the mapping of soil, crop, and water conditions. GPS receivers, either handheld or mounted on machinery, help users return to specific field locations for targeted sampling or treatment. The data recorded in the field, such as weed patches or crop health observations, can be integrated into GIS and other analytical tools to enhance data sets and improve decision-making processes. Accurate GPS-based data also improves processes like image classification, contributing to better analysis and resource management. Applications of GPS in precision agriculture. The main applications of GPS in precision agriculture include 1. Field mapping and soil sampling. GPS enables accurate field mapping and digital land representations. Combined with soil sampling data, it provides insights into soil variability, helping farmers create precise nutrient management plans for optimal fertilizer application. 2. Variable rate applications. Using GPS, farmers can create prescription maps to guide machinery in applying inputs like fertilizers and pesticides at varying rates, tailored to the specific needs of different field areas. This targeted approach minimizes waste and reduces environmental impact. 3. Automated steering. GPS-enabled automated steering systems ensure machinery follows predefined paths with high accuracy, reducing operator fatigue, minimizing human error, and improving efficiency. 4. Yield monitoring. GPS technology facilitates the accurate measurement and mapping of crop yields, enabling farmers to identify high and low yield areas, investigate underlying causes, and implement strategies to enhance productivity. 5. Crop health monitoring. GPS-integrated sensors collect real-time data on indicators such as chlorophyll levels and canopy temperature. These insights allow for early detection of stress or diseases, enabling proactive measures to mitigate crop losses. Geographic Information Systems, GIS. GIS are software tools designed to allow users create, overlay, and analyze multiple map layers, manage associated data, and enable spatial analysis. Common GIS software includes ArcGIS and MapInfo, along with GIS-integrated components in many farm management platforms. These systems play a pivotal role in PA, helping farmers manage spatial data to make informed decisions. Farmers can utilize GIS to analyze a variety of data layers, such as soil type, topography, crop yield, field boundaries, management zones, remote sensing imagery, and pest or weed locations, and historical land use. Recording and analyzing this information over time allows farmers to track variables like soil, yield, and elevation, which can then be used to create management zones. When digitized, this data can generate variable rate prescriptions that integrate directly into GPS-enabled tractor systems, streamlining site-specific crop management. Using the results of soil sampling and testing, soil properties maps can be created through interpolation. These maps are then used to generate prescription maps for variable rate fertilization, a key aspect of PA. A prescription map is a geo-referenced map which contains rate information so that variable rate controllers can apply the appropriate application to the appropriate location using real-time GPS sensor information, thus, a digital map that provides specific recommendations for different areas of your field. To create the prescription map, we need to collect and fuse data from various sources like soil sensors, satellite imagery, and drones to create detailed maps. This approach not only reduces fertilizer usage, but also enhances both economic and environmental outcomes. GIS empowers farmers to precisely monitor and address field-specific needs, resulting in higher yields and optimized resource use. For example, by identifying low-yielding areas, farmers can implement targeted interventions, such as nutrient application or irrigation adjustments. This precise approach enhances efficiency and reduces resource wastage. Using GIS technology, farmers can precisely map and analyze soil properties, moisture levels, and nutrient deficiencies. By accurately assessing the needs of each field, farmers can apply fertilizers and pesticides in the correct quantities and at the optimal time. This targeted application not only lowers costs, but also reduces the risk of nutrient runoff and contamination of nearby water sources. We have come to the end of the second part of this module. Stay tuned for the next part.